In this video, we're going to move on to chapter 3 of the book. Particularly, we'll look at section 3.1. And the really important content from this section is to make sure that we're all on the same page regarding two key definitions. The first is what exactly it means to model something as a particle. And the second is what it actually means for a body to be in equilibrium. So we talked about this particle idea a little bit back in chapter 1, if you can remember back to a few weeks ago. And the key point was that as we approach problems from an engineering point of view, we want to get an accurate answer, of course. However, it's important that we kind of take the most efficient approach to our analysis that we can. And what will happen is, under certain loading scenarios for certain geometries, when a body is acted upon by forces, we can just kind of ignore the physical dimensions of that body and just treat it as such if all actual forces were acting on a single point on the body. We can actually model it as a particle. So it's hard to see what this means until you actually start to work a few problems. So for now, just try to keep in mind some kind of key memorization points that we'll keep referring back to as we actually start to analyze some rigid body problems under a particle model in the text. And the first point is that just because we model something as a particle, it doesn't mean that it's necessarily small. The second point is when we model something as a particle, even though we're going to kind of throw away the dimensional information of the body and kind of act if all the forces were acting at a single point, we're still going to consider the mass of the body. It's not like we're ignoring everything physical about the body. In addition, when you have a body that's acted upon by forces, it may happen that in certain scenarios you can model it as a particle, and in certain you can't. It all depends upon the way or the nature of the forces as they're distributed across the body. And particularly, we're always going to be able to do a particle model whenever all of the forces act on what is known as concurrent on the body. And what that means is that their lines of actions intersect at a single point. So think about this kind of pulley or wheel that is kind of resting along this inclined plane at a specified inclination of 30 degrees, and say that there is a force exerted on it by a cable, someone pulling, and we'll typically refer to forces that are exerted by a cable as tension forces. So what do we notice here? Well, if I were to extend the line of action of both the tension force along with the force that is exerted by the surface on this actual wheel itself, you'll notice that as we'll cover a little bit more detail later in this chapter, actually, there's always going to be a force that a surface exerts on a body, which is perpendicular to the surface itself. We call that the normal force. Notice that if the actual plane that this is resting on is elevated by 30 degrees, then kind of the angular separation between the vertical and the normal force is also going to be 30 degrees as well. And then in addition, of course, we have the actual weight of the actual wheel itself, which we'll always model as initiating at the center of gravity. We haven't defined what that is yet, but for a symmetrical situation like this, it'll just be kind of at the intersection of the two lines of symmetry or right in the middle. So notice if you draw the line of action of all those forces, the weight vector is perfectly vertical. The tension vector, if I were to extend that line, it goes right through the middle as well. Same thing with the normal force. If I were to draw it upwards vertically, that line would go right through the center of the wheel. So in the case that when all the lines of actions of all the forces acting on a body go through a common point, we say that those forces are concurrent and we can use a particle model. Now, if you've studied physics at all or kind of know what's coming ahead, what this really means is that there's not going to tend to be any net torque on the body. It's not going to rotate. All of those forces, if they weren't to counterbalance, which they will for our case, since we're dealing with statics, where all forces will be where all bodies will be in equilibrium, and what that means is that there's no net or resultant force. What we will find is that if there were to be a resultant force, it would only cause translation. It wouldn't cause rotation. So there's no torques acting on the body that need to be counterbalanced. So hopefully that makes sense to everyone. Particle doesn't necessarily mean it's small. We can do a particle model whenever all the forces are concurrent, which means that the lines of action of the forces interact at a single point. So what does it mean for a body to be in equilibrium? Well, really what that means is that Newton's second law, the sum of all forces, is equal to zero. It doesn't necessarily mean that the body is stationary. So what that means is that a body is going to be in equilibrium when the acceleration is zero. Remember that the acceleration is the time rate of change or the derivative of the velocity. So that just means that the velocity is not changing. The magnitude of velocity is nothing more than the speed. So it could mean that the body is actually at rest. If I'm just sitting here and I'm not moving, my speed is not changing. In both cases, initial and final, it's zero. However, it could also mean that a body is moving at a constant velocity as well. We won't deal with many of this second scenario. The majority of equilibrium scenarios we deal with will be the first case, where a body is actually stationary. But notice that if we define equilibrium as the absence of acceleration, then Newton's second law will simplify to the sum of all forces acting on a body, and there can be an arbitrary amount, just say n. We'll call that vector sum of these forces the resultant force. It must be equal to 0 if a body is in equilibrium. So the key point there is equilibrium doesn't necessarily mean stationary. Equilibrium means that a body is not accelerating, which means it's either stationary or moving at a constant speed. So hopefully those two definitions kind of kicked off some dust from either chapter 1 or prior in your physics class, and I will see you in the next video.